AP Chemistry. We are starting a one-lesson unit on the subject of the geometry of molecules, and it goes by the name VSEPR or VSEPR. So VSEPR stands for valence shell electron pair repulsion, and you'll see as we do it what that name means. So VSEPR provides a set of rules by which the three-dimensional geometry of a molecule can be determined by its Lewis dot structure. According to the VSEPR model, bonding domains space themselves at equal lengths, and non-bonding domains, that is lone pair electrons, repel bonding pair electrons to change the bond angle. So let's go through some definitions. An electron domain is anywhere a pair of electrons exist. At least one pair of electrons exists. An electron domain can be a lone pair, a single bond, a double bond, or a triple bond. Any of those four are considered to be one electron domain. A bonding domain is an electron domain that bonds two atoms, that connects between two atoms. A bonding domain can be a single bond, double bond, or triple bond. So the only one it can't be is a lone pair, because that does not bond between two atoms. A bond angle is the angle that two terminal, remember the word terminal means outside, two terminal atoms make with the central atom. So there's the central atom in pink, and those are terminal atoms. They're on the outside, and that's the bond angle. So that's the configuration is going to determine what that angle is, and you're going to see how we do that. We're going to go through all of the major domains for molecular geometry. Okay, so let's go over and let's be sure we understand what kind of domain each one of these is. So an electron domain is anywhere a pair of electrons exists. A bonding domain is an electron domain that bonds two atoms. So right there you have a double bond. That is one electron domain and one bonding domain. Even a double bond is just one domain. And basically the word domain means a place. So it's a place where two atoms are being bonded. That is one electron domain and one bonding domain, that other double bond. That lone pair there is an electron domain and a non-bonding domain. It doesn't bond two atoms together. Same with that one. It's electron domain and non-bonding domain. Same there. And same there. So every one of them is an electron domain. Over here, that electron domain and a non-bonding domain. That's one electron domain and one bonding domain, even though it's a triple bond. It's just one domain, one place where two atoms are being bonded. And finally, the single bond between carbon and hydrogen. It's an electron domain and a bonding domain. The formula for molecular geometry has three parts. A represents the central atom in the molecule. Xn represents the number of bonding domains. And En represents the number of non-bonding domains, that is lone pairs. So here's an example. AX2E1. This is a molecule with a central atom A and three electron domains. You just add up the numbers at the bottom. That's the total number of electron domains. Two of the domains are bonding domains, those are the X's, and one is a non-bonding domain, that's the E. That would be a lone pair somewhere on the molecule. The domain geometry shows all domains as bonding domains, and the molecular geometry shows both bonding and non-bonding domains. So you'll see what that means as we get into some examples. Okay, so here we go. We're going to get started with the simplest. Well, actually, the simplest is not shown here. The simplest would simply be two atoms, like O2, N2, H2. Those would be diatomic molecules. They can only have one shape, right? There's they're set side by side, and there's a straight line between them. So we're not going to deal with that. We're going to go on to where we have 3 atoms in the molecule. So the first one is an AX2E0. So that means it has 2 bonding domains. That pink-white tube between the atoms is basically the bond, and it represents 2 electrons. It represents an electron, or a bonding domain, rather, I should say. And when you don't have any lone pairs, you see the E0 means there are no lone pairs, then those 2 bonding domains are going to separate as far as they can. They're going to get as far away from each other as they can, those electrons on each side. And so that's going to be a 180-degree angle. So the domain geometry, which is basically the family name, you'll see what I mean when we do a few more examples. It's the name of the family, and the molecular geometry is the actual name of that particular configuration, that molecule. So when there are no lone pairs, there's only bonding domains, there's no non-bonding domains, then the domain geometry name and the molecular geometry name will be the same. Again, you'll see what I mean by that when we get to some more examples. Okay, so a linear domain geometry means that the molecule has 2 electron domains. The molecular geometry is also linear since both are bonding electrons. The molecule is a straight line and has a 180-degree angle. Note, when there are only bonding domains, as there is in this case, in a molecule, the domain geometry and the molecular geometry will be the same. They'll have the same name. So that's an example. An example of this is carbon dioxide, CO2. The carbon's in the middle and the 2 oxygens on each side with double bonds in between them. It doesn't matter how many bonds it is. It's a domain. All right, so that's the simplest that we can do. So let's move on. Okay, now we're going to go on to where we have 3 domains. So the domain geometry means trigonal planar means that it has 3 total domains. They could be bonding, they could be non-bonding. So in this example right here, you see that all 3 of them are bonding. AX3, meaning they're all bonding. You don't have any non-bonding. That's the E0. And we said that when that happens, the domain geometry and the molecular geometry will have the same name. Now, as I mentioned before, the domain geometry is really the name of a family. It's all of the molecules that have 3 electron domains, whether they're bonding or non-bonding. Trigonal planar molecular geometry is specifically the geometry of this specific molecule, and it means that it has 3 bonding domains and no lone pairs there. When there are lone pairs, I will show them. You will see them on the screen. So let's read this. So a trigonal planar domain geometry means that the molecule has 3 electron domains. That's the total of bonding and non-bonding together. The molecular geometry is also trigonal planar because all 3 are bonding domains. The molecule is flat and has 3 120-degree angles. So you know from geometry, 3 times 120 is going to give you 360. You have 360 degrees when you go around a circle. The name means that it has the shape of a triangle and is entirely on the same plane. It's flat. You could lay it on a table, in other words. Again, read this again. Note, when there are only bonding domains, as there are here in the molecule, the domain geometry and the molecular geometry will be the same. Okay, now we're still in the domain geometry of trigonal planar. Remember I said that's the family. That's the molecules that have 3 total electron domains, whether they're bonding or non-bonding. Here we have a situation where you have 2 bonding, that's the AX2, and 1 that is non-bonding or lone pair, that's the E1. And what you see happening here is that lone pair on top, and this is really the key point to this. Well, let's go down and read this and we'll talk about it. So a trigonal planar domain geometry means that the molecule has 3 electron domains. That's the same as the last molecule. There are 2 bonding domains and 1 non-bonding domain. This results in a bent molecule. A bent molecule forms when 2 atoms form an angle with the central atom. The non-bonding lone pair electrons repel the bonding electrons. This pushes the angle from 120 degrees, which you saw in the last molecule. It squeezes it down. It makes it tighter. In other words, when you had an atom up there on top, it not only had electrons, it had protons. And those protons, in a sense, kind of cancel out the electrons. And so on the trigonal planar molecule in the previous slide, you had 3 molecules and there was a 120 degree angle between the bonds. Now you've taken away that atom, you only have the electrons left behind. You don't have the nucleus with the protons anymore. So you have just a pure negative charge up on top. So what that's going to do is that's going to push hard on those 2 tubes down below, which represent the bonding domains between the central and terminal atoms. So it's going to squeeze that bond down from 120 down to 119. And that shape is called a bent molecular geometry. So the lone pair pushes down on the bonding electrons. This reduces the bond angle. Okay, now we're going to move on to a new family, the Tetrahedral family. A tetrahedral domain geometry means that the molecule has 4 electron domains. There are also 4 bonding domains in this particular molecule. This results in a tetrahedral molecular geometry, and all 4 of the bond angles are 109 degrees. So again, that note down below, when there are only bonding domains, as there are here in the molecule, the domain geometry and the molecular geometry will be the same. So the tetrahedral family, the tetrahedral domain geometry, means there's 4 electron domains, either bonding or non-bonding. Tetrahedral molecular geometry specifically means all 4 are bonding. You don't see any lone pair there. So that's AX4 for the 4 bonding domains, and E0 meaning there's no lone pair or non-bonding domains. And that's a methane molecule, that's CH4. And it does have a 109 degree angle in between all 4 of the bonds. So you could turn that molecule in any direction, so any of those outside white atoms are up or pointing up, and it would look exactly the same. It's perfectly symmetrical in all directions. Okay, now we're still in the tetrahedral family, the tetrahedral domain geometry, meaning we have a total of 4 electron domains. But if you look at the formula, you see that we have 3 that are bonding, that's the X3, and 1 that is non-bonding or lone pair. And that's called a trigonal pyramidal, or you can say pyramidal if you want. So let's read. A tetrahedral domain geometry means that the molecule has 4 electron domains. 3 of the domains are bonding domains, and 1 is a non-bonding domain. This results in a 3-faced pyramid-shaped molecule. This has the name trigonal pyramidal. That's because it forms a triangle, but it forms a pyramid. It's hard to tell on this image, but it's not flat. It is not flat. That central atom is up above the 3 white terminal atoms, so it's forming a 3-sided pyramid. The 3 bond angles are less than 109 degrees because the non-bonding pair, that lone pair up on top, pushes down on the 3 bond domains. So up there in blue it says the non-bonding lone pair pushes down on the bond angles. And that's an example. That example is ammonia. So those angles are all less than 109 degrees. So here's the general rule you'll start to see, is that if you have atoms on all 4 of the domains, or all bonding domains, like CH4 was in the previous slide, they'll space out equally. Now, if you put lone pairs up there, it's going to squeeze down. Remember, those pink-blue tubes are electrons, and the lone pair is going to push down on them, and it's going to squeeze them down together so that they're closer together down below, and that means you're going to have less than a 109 degree angle between those. Okay, now we're still in the tetrahedral family, this tetrahedral domain geometry, and now we've taken away 2 of the atoms. So now we have 2 bonding domains, that's the X2, and 2 lone pair, and that results in a bent molecular geometry. And the example of that is water. A tetrahedral domain geometry means that the molecule has 4 electron domains. When 2 of the domains are bonding domains and 2 are non-bonding domains, it results in a bent molecule. Now, it's not a bent molecule that has exactly the same bond angle as the bent molecule from the trigonal planar that we saw a few slides back. It's still called bent because it looks like that, but it's a different situation. Here you have 2 lone pair, and in the trigonal planar a few slides back you only had 1 lone pair up on the top. This bent geometry has a different bond angle than the trigonal planar bent geometry. This is the geometry of a water molecule, and it produces, and this is a very well-known number when you study chemistry, a 104.5 degree bond angle. That's 4.5 degrees less than the full 109 degree tetrahedral bond angle when we had the CH4 where all were bonding domains. So the non-bonding lone pair pushes down on the bond angles down below. So that's the theme of this whole, again, the theme of this entire lesson is that if you have just bonding domains, they want to spread out as equally as possible so they all have the same angle. The moment you take away an atom and just have a lone pair, it squeezes those bond angles down so that they're smaller than they were before. Now we're going on to a new family. This is called Trigonal Bipyramidal, or you can say Trigonal Bipyramidal is fine. Trigonal Bipyramidal, you'll notice, has 5 electron domains. And there you see them right there. So let's go on down and read this. So a trigonal bipyramidal domain geometry means that the molecule has 5 electron domains. All 5 domains in this case are bonding domains. This results in 2 3-sided pyramids. One is an upright trigonal pyramidal and the other is an inverted or upside down trigonal pyramidal. So go back and look at the trigonal pyramidal we had a few slides back. It was a 3-sided pyramid, and you see that on the top half of this molecule. The 3 E's are the base of the pyramid, and the A is the top of the pyramid. It's a 3-sided pyramid. But you also have a 3-sided pyramid down below. It's upside down. The A is the top of the pyramid, except it's upside down, and the E's are also the base. So you have 2 3-sided pyramids stuck one on top of the other, with one right side up and one upside down. So the bond angle between the equatorial atoms, so let's define that. The equatorial atoms are the ones that say E. They're around the equator of this molecule. And the axial atoms are the ones A. That's like the North Pole and South Pole, if you want to think of it in those terms. And those are called axial. So the bond angle between the equatorial atoms is 120 degrees between all 3 of them. That would equal 360. And then the bond angle between the axial and equatorial atoms is 90 degrees. All right, so this is trigonal bipyramidal. It means triangle, a triangular pyramid, and bi means you have 2 of them. So that's, and that's the family is trigonal bipyramidal. That's the domain. So we're going to see some more from that family right now. All right, now we're still in the trigonal bipyramidal family. That means we're going to have 5 electron domains. This time, though, 4 of them are bonding and 1 of them is a lone pair, as you can see. And that molecular geometry is called a seesaw. So let's read this. A trigonal bipyramidal domain geometry means that the molecule has 5 electron domains. 4 of the domains are bonding domains and 1 is a non-bonding domain. This is called a seesaw. The molecule is turned on its side to look like a seesaw. So they pulled a fast one on you here. You got to see what they did. They took away one of the equatorial atoms, and then they turned the molecule on its side. So they did a little sleight of hand here. So what you have now is where that lone pair is where one of the 3 equatorial atoms was. The 2 on the right, the one on the right and the one on the left are both axial. And so you see that marked down below. So all 4 bonds are pushed downward. That lone pair is pushing all the bonds downward. So that the 2 equatorial atoms are less than 120 degrees. Remember, they were 120 when you had all were bonding domains in the previous slide. And the 2 axial atoms are less than 180. We said they were 90 between themselves, the axial and the equatorial, but now they're pushed down. So we're talking about from axial to axial. It's a 180 degree angle, but you're pushing those down, so it's less than 180. So the non-bonding electrons push the axial atoms down, producing a bond angle of less than 180 degrees. The equatorial atoms are pushed together to form an angle less than 120 degrees. So just think of all of those arms being pushed down slightly so the bond angles get small. Okay, so we're still in the trigonal bipyramidal family, domain geometry. which means 5 electron domains total. So here you see that 3 of them are bonding, X3, and 2 of them are lone pairs. You see those up on the top of the image up there. And that logically forms a molecule called a T-shape. So let's read this. A trigonal bipyramidal domain geometry means that the molecule has 5 total electron domains. If 3 of the domains are bonding domains and 2 are non-bonding, this produces a T-shape. So what's happened here is 2 of the equatorial atoms have been removed. The 2 non-bonding electrons pairs push both bond angles down to form angles less than 90 degrees. So those two, they look like they're sticking straight out because I can't change this. It's an image that I grabbed off the internet. I can't change it, but they should be kind of bent down or angled down. Those two with the A, the 2 axial, they should be angled down a little bit. So the non-bonding electrons push the axial atoms down, producing a bond angle of less than 180 degrees or less than 90 degrees on each side, in other words. Okay, we're off to our last family here, and that's the octahedral. An octahedral has 6 electron domains. So you can see that the actual octahedral molecule is AX6E0. It has 6 different bonding domains. An octahedral domain geometry means that the molecule has 6 electron domains. When all 6 are bonding domains, the molecular geometry is called octahedral. All bonds are at 90 degrees. So it doesn't really matter which ones you call equatorial and which ones you call axial. You could turn any one of those terminal atoms up to the top and the molecule would look exactly the same. Everything's 90 degrees. Okay, so all bond angles are 90 degrees. Now we're still in the octahedral family, but we've taken away one of the atoms. So now we have AX5E1. We have 5 bonding domains and 1 non-bonding domain, and that's called square pyramidal. And you can see why. If you put faces onto that molecule, you would have a 4-sided pyramid. So that's the square pyramidal. So an octahedral domain geometry means that the molecule has 6 electron domains total. When 5 are bonding domains and 1 is a non-bonding domain, the molecular geometry is square pyramidal. The non-bonding electron pair pushes the 4, you can call them equatorial since they look like they're around the sides, pushes the 4 equatorial bonding domains, those are the E's, upward toward the axial electron. So you see how that works. The lone pair, they naturally form a nice square pyramid with a flat bottom. But now the bottom's not flat because the lone pair electrons are pushing all 4 of those bonding domains where the E's are upward slightly. So that's going to be the shape, but it's still called a square pyramidal. So equatorial bond angles are 90 degrees. That didn't change because the electrons aren't pushing the E's together. It's just pushing them upward. I take that back. It's slightly less than 90, but we can still call it 90. It does slightly go down a little bit. The bond angles between the equatorial bonds and the axial bond is less than 90 degrees. Okay, so again, all of those E's are going to be sloped upward a little bit towards the A. And one last one. On this one, we're still in the octahedral family. We have 6 electron domains. 4 of them are bonding, that's the X4, and 2 of them are non-bonding, those are lone pairs, that's the E2, and that's called square planar, and you can see why. It's a square, and it's flat, it's on a plane. So an octahedral domain geometry means that the molecule has 6 electron domains. When 4 are bonding domains and 2 are non-bonding domains, the molecular geometry is square planar. All 4 bonding domains are on a flat plane. The non-bonding electron pairs push the bonding domains equally on the top and on the bottom. For this reason, the molecule is flat. So if you look at those 2 lone pairs, they really should be directly above and below each other, but I drew one of them kind of out to the side so you could see it. But the one on the top is pushing those 4 bonding domains down, but the one on the bottom is equally pushing them back up. It's the only time in a molecule structure where you'll have lone pairs that don't change the angle of the molecule. They keep it the same because you have equal and opposite electron pairs. So equatorial bond angles are 90 degrees. That's around those 4 atoms there. And non-bonding electrons on top and bottom provide equal and opposite force on the bonding domains. So You push up with the equal force, you push down with the equal force, and you still have a flat molecule. Okay, we know that atoms ionize in whole number units. So cations take on charges of +1, +2, +3, and so on, such as sodium, it's a +1. And anions take on charges of 1-, 2-, 3-, and so on, such as chloride. So polar molecules such as H2O have a positive side and a negative side. We talked about that way back in the foundations unit. Oxygen is more electronegative than hydrogen, so the electrons are pulled in the direction of the oxygen atom. So the positive pole is symbolized by delta plus, that's a lowercase Greek letter delta, and the negative end is symbolized by delta minus. So you've seen those symbols before way back. And it just means water's an electrically neutral molecule. It has just as many protons as electrons overall, but the electrons tend to be pulled over to the oxygen side. So that side is more negative, whereas the hydrogen side is more positive. Another way to represent a polar molecule is with an arrow pointing toward the negative side and a plus sign on the positive side. So those are two ways to represent a polar molecule or a dipole. So what is a dipole? Dipole moment is a way of quantifying, giving a number value to the polarity of a molecule. Dipole moment is represented by the letter mu, pronounced mu. So in other words, we always could put a number to ionic charges. They were +1, +2, or -1, -2. But with polar molecules such as water, we just said, the oxygen side's kind of a little bit on the negative side, and the hydrogen is a little bit on the positive side, but we never put a number to it. So now this gives us a way to put a number to a polar molecule to tell you how polar it is. So dipole moment equals the charge between two particles times the distance between them. And that symbol there is mu equals QR. So mu is the dipole moment, Q is the charge between the two particles, and R is often used for distance rather than the letter D. So R is the distance between the two particles. It's often used in physics and chemistry. So R is the distance between the two particles. It could be, say, a proton and an electron, or two protons, some type of charged particles. The unit of measure for dipole moment is called a debye. 1 debye equals 3.34 times 10 to the minus 10 coulomb times meters. So coulomb is the unit of charge that you see in the formula, and meters is the unit of distance that you see in the formula. I don't think you'll ever hear the word debye again in this class, but you should understand a dipole moment. They could ask you a multiple choice question on it to see if you even know what it is. They will not ask you to do a calculation, but we're going to do one just to gain a little more insight into what it is. So example, what is the dipole moment of an HCl hydrochloric acid molecule with a bond length between hydrogen and chlorine of 1.27 angstrom and a charge on each atom of 1.60 times 10 to the minus 19th? Okay, so that last number, 1.60 times 10 to the minus 19th, is a number we encountered earlier, but you're not expected to have it memorized. It's the charge on an electron or the charge on a proton. Could be either one. They have the same charge. Okay, so what is that funny A with the little circle above it? That's called an angstrom and is equal to 10 to the minus 10 meters. All right, so if you remember when we talked about different exponents, 10 to the minus 9 is called a nanometer. 10 to the minus 12 is called a picometer. So why did they feel they had to have something in between 10 to the minus 10? And it's simply because small atoms usually have distances or bond lengths in that order of 10 to the minus 10. Okay, so remember, 10 to the minus 9 is 10 times bigger than 10 to the minus 10. So they felt 10 to the minus 10 was a better number to work with when you're working with small atoms, and angstrom is the name of a Swedish chemist. Okay, so that's what that means. And the equivalency is 1 debye equals 3.34 times 10 to the minus 30 coulomb meters. So that's a really tiny number. So there's the formula. So now we're going to plug in, and I'm just going to give you one of these to do just so you understand the concept of dipole moment, and then we will hardly ever talk about it again. So there's mu, that's dipole moment, equals the charge. That's the Q in the formula. And there is the R, and that is the bond length between the chlorine and the hydrogen. So it's 1.27 angstroms. But we're no good at working with angstroms, so we need a conversion. So we have an equivalency up there. We know that 1 angstrom equals 10 to the minus 10 meters, so we're going to plug that in so that angstroms cancels out, and we're now working in meters, 10 to the minus 10. Okay, and then finally, we have our equivalency between a debye and coulomb meters, and it looks like kind of a mess of a formula, but we're going to go ahead and cancel. Coulombs cancels with coulombs, angstroms cancels with angstroms, meters cancels with meters, and the last man standing is debye. And so you multiply everything on the top, divide everything on the bottom, and you get 6.08 debye. Again, there's no way they would ask you to do a calculation like this on the AP, but they would expect you maybe to know what a dipole moment is and what the number means. So what does it mean? So a dipole moment assigns a numeric value to the polarity of a molecule. More polar molecules have larger dipole moments. That's what you really need to understand about the dipole moment. Okay, that takes care of this lesson. It's a one lesson unit on the molecular geometry. We're going to move on to a really big and important unit coming up in about 2 or 3 days. You have more than 1 day to finish this lesson, but it should take you maybe 1 day to do it. So get it done as soon as possible. Get caught up on your other assignments. And what I will do is have those assignments ready for you if you need some old assignments. Okay, that takes care of it. We'll see you on the next lesson.